So in today's video we are going to be going over separable differential equations. We'll first touch down upon the intuition behind the formula for separation of variables, and then after that we'll be going into practical examples that includes finding general solutions to differential equations. Now what you're about to see here is condemned by many mathematicians, but I think it's a very good tool for building intuition behind the formula we're going to utilize in our examples. So consider we have an equation dy over dx is equal to x times y. Now normally you would want to integrate on both sides, but you cannot do that because you cannot integrate xy with respect to one variable. So what your end goal is to do here is to separate the variables, get y dy on one side and x dx on the other side. So to do that we can multiply by dx on both sides. Now dy dx is not a fraction, that's why this is condemned by many mathematicians. But in this scenario we'll just assume that we can do this. So on the left hand side the dx's will cancel out, on the right hand side we'll get xy dx. Now the only thing left to do here is divide by y on both sides to move the y to the other side. So after we do that, on the left hand side we'll get dy over y, and on the right hand side we'll get x dx because the y's will cancel out. And from here we can integrate on both sides of the equation, giving us the integral of 1 over y dy equal to the integral of x dx. And the last thing left to do here is replace y with any function of y. We can note it as p of y. And then on the right hand side we can replace our x with any function of x, naming q of x. And what we've just found here, this formula, is what we call the formula for separation of variables. And we'll use this formula oftentimes in our future examples. So now consider the differential equation dy over dx is equal to x over y. Now we're going to go into some mathematical definitions here. So for this equation dy over dx is equal to x over y, this equation is written in the form p of y times q of x. Now whenever we have such a form of a differential equation, we can rewrite that equation in the form of the integral of 1 over py equal to the integral of q of x dx. This is what we've proven or what we've derived in the previous section of the video. So now we can move this formula to the side because we will not need it just yet. What we need for now is to identify q of x and p of y for our equation. So we can rewrite our equation in the form of dy over dx is equal to x times 1 over y. And here we can clearly see that p of y is the only expression in terms of y, so it will be 1 over y. And q of x is the only expression in terms of x, so that will be x. We can highlight them in colors. And then let's rewrite them in the corner of the screen, just for simplicity. And now at this point of the equation, we can substitute it into the formula. So the left hand side will get the integral of 1 over y, which is the integral of 1 over p of y, equal to the simply integral of x, because x is equal to the q of x. And now the left hand side integral can be simplified into just the integral of y dy, because 1 over y is simply y, it simplifies. And now we can clean up the screen because we'll no longer need the q of x, p of y, and p of y functions because we've already utilized them. And now just for the first example, we can change this formula in the corner into the power rule of integration, because that's the only formula we need to complete this integration. So now we can apply this formula to the integrals, and we'll get the integral of y squared over 2 plus c1, where c1 is a integration constant, equal to x squared over 2 plus a different integration constant, c2. Now, when you want to find general solutions, you would want to get only one constant in the end, so we need to subtract c1 on both sides of the equation. And now on the left hand side we'll get just y squared over 2, since the c1 and c1 minus c1 simplifies. And on the right hand side we can denote a new constant c3. Now at this point we can simply get rid of the denominators, so we can multiply both sides of the equation by 2. And on the left hand side we'll get just y squared. And on the right hand side we'll get x squared plus c3, because a constant multiplied by constant is again just a constant. We can treat c3 times 2 as a new constant c4, but we don't really need to do that. And lastly, we can move the x to the other side to recognize this as an equation of the circle. Now, normally you would try to rearrange for y, but this is a very special case where this is a result of differentiation of an equation of a circle. So now we'll do just one more example. Actually, we'll do two more examples. So this equation dy over dx is equal to x times y. We've already solved this equation partially when we were deriving the separation of variables formula, but I think it's nice if we finish it off by finding the general solution to the equation. So the same as before, we will need the separation of variables formula, but what we'll also need is our q of x and p of y. So we can rewrite this equation as dy over dx is equal to x times y. And now we can see that x is the only expression in terms of x and y is the only expression in terms of y. So q of x is equal to x and p of y is equal to y. And now we can substitute into the formula. So the integral of 1 over y, because p of y is y, dy is equal to the integral of x dx. Now we can just integrate, there is no way to simplify those integrals. So we'll get the natural log of y plus c1 equal to x squared over 2 plus c2 after completing the integration process. Now from here we can again simplify the constants by subtracting c1 on both sides. So on the left hand side we'll just get ln y, since c1 minus c1 is equal to 0. And on the right hand side we'll get another constant c3 just as before. Now what your intuition tells you to do here is to multiply by 2 on both sides to get rid of the denominator, but you would end up with a root, and when finding general solutions you want to avoid roots. So what we can do now is we can simply put everything in the exponent of e to cancel the natural log on the left hand side. And again, on the left hand side the natural log will cancel, and so will the absolute value, because e raised to any number or any function will always be positive, so we no longer need the absolute value. And then on the right hand side we can split the exponent along the addition, just rewrite it as y equal to e to the x squared over 2 times e to the c3. And e to the c3 is again a constant, so we can rewrite it as a different constant, new constant. And generally we want to rewrite it as a one letter constant like a, just because it looks nicer than c sub 4 multiplied by e to the x squared over 2. And now we can rewrite it again as y equal a e to the x squared over 2. And that is our general solution to this differential equation. Now, the last example for today is finding the general solution to the differential equation dy over dx is equal to y cos x. Now, even though the function of x here is a trigonometric function, the way of solving this equation doesn't vary at all from what we've done before. So again, we can rewrite this equation as dy dx is equal to y times cosine of x. And from here we can identify y as p of y and cos of x as q of x. And we can rewrite this equation using the separation of variables formula as the integral of 1 over y is equal to the integral of cosine of x dx. Now here these integrals are again unsimplifiable, they are in the final forms. So we'll just have to integrate. On the left hand side we'll get the natural log of y plus c1 equal to the sine x plus c2, because the integral of cosine of x is sine x. Now the process repeats itself from here. We subtract c1 on both sides of the equation. On the left hand side the constants simplify, so we'll just get ln y equal to the sine of x plus a different constant c3. And we'll put everything into the exponent of e. And after simplifying the left hand side, we'll get y equal e to the sine x plus c3. And the constant c sub 3 can be brought down and multiplied by e the same way we did before. So we can rewrite this as a e to the sine of x. And this is our general solution to this example.